I'm not sure if you've ever heard of a centaur, a very weird figure in mythology. A centaur is a half man and a half horse. Well, today we're going to learn kind of a mathematical equivalent of this. We're going to study today what's called piecewise functions. And piecewise functions are a way to draw graphs that are half one type of function and half another type of function. Here, this piecewise function g of x, actually half of it, roughly half of it, is a parabola, and the other half of it is a line. And this is achievable through what's called a piecewise function. Now you may be wondering, Mr. Klein, what would this ever be used for in real life? Well, here's an example. I don't know if any of you have ever been skydiving, but imagine what happens to a skydiver. A skydiver jumps out of an airplane at a very high elevation, and they fall according to the acceleration of gravity, just in a free fall. Well, that's modeled by a parabola. But at some point before the skydiver hits the ground, they're going to open up their parachute, and then they're going to fall steadily via the parachute, and that's modeled by a linear function. Here, to model this skydiver's fall from an airplane, we need a piecewise function. I know many of you have probably never been skydiving, but even imagine getting in your car. When you hit your accelerator in your car, that's modeled by a parabola because you speed up as you go. When you hit the cruise control in your car, now you're being modeled by a line. When you hit the brake in your car, now you're decelerating. That can be modeled with a square root. So here's our first example of a piecewise function that we're going to graph by hand. If you have a printer, I encourage that you print out some graph paper that you can graph this with. But a common characteristic of a piecewise function is going to have multiple rows. In this case, we have 2 rows. And then those rows are going to be joined together by a brace. Now, the things I really want to make this description a little bit easier, I'm going to call the top row the red row, or the red rules, x plus 2. And I'm going to call this bottom row the blue row, x minus 1 squared. But then over here, to the right of these semicolons, I'm going to highlight these in green. These are called the conditions of each row. We're going to follow the red rules anytime x is less than 1, and we're going to follow the blue rules, or the blue equation, anytime x is greater than or equal to 1. Now, I like to think of these conditions as building a fence on your graph, okay? You know what fences are. They're used to distinguish 2 properties from each other. So since my conditions right here center around this number 1, what you're going to do first on your graph is draw a dotted vertical line that I'm calling the fence, and it's going to cross through 1 on the x-axis. And then what this fence does is this fence is claiming that everything to the left of the fence is going to follow the red graph. Okay, I'm going to call it the red region. Everything to the left of this fence is where x is less than 1. That's called the red region. And then everything to the right of this fence, we're going to call the blue region. This is where x is greater than or equal to 1. So let's graph this red region first. This red function here is a line, x plus 2, or you can write 1x plus 2. And you graph a line, the easiest way to graph a line is by its y-intercept, which is 2, and its slope, which is 1. What we're going to do is we're going to start our graph with a point at 0, 2. That's called the y-intercept. Let me get my red marker here. So 0, 2 is the y-intercept. And then we're going to follow the slope of 1. We're going to write it as a fraction, 1 over 1. This line has a rise of 1 and a run of 1, and we're going to draw another point. Now I'm going to kind of keep drawing points here across into the other end of the line. A slope of 1 over 1 can also be reversed, meaning we can also take this slope down to the left, down 1 and left 1. Now right now I've drawn my entire line, but think about what you know about this fence. In reality, this line is only allowed to exist in its own region to the left of the fence. So this is what the entire line would look like, but the only part that I'm going to show on my graph, let me pull out my eraser here, is whatever falls to the left of this fence. Here I've drawn this red rule, and it exists only to the left of my fence. Now let's consider this blue equation. So this blue equation has the x squared. It's going to be called a parabola. And we just learned this in the last couple of lessons, how to graph a parabola. This particular parabola is going to have a vertex at 1, 0. And it just has an a value of 1. It's just going to be a standard parabola um, with a standard steepness. And listen, I don't expect this parabola to be drawn perfectly. So in reality, this parabola would exist to the right of the fence. If there was no rules in place, no boundaries or fences, this parabola would look like roughly like this. Okay, but because of my fence and because of this is a piecewise function, I know that this parabola is only allowed to exist in the blue region. So even though the parabola as a whole would look like this, let me hit the undo button. The reality is I'm only going to draw it to the right-hand side of the fence. Okay, now the last thing I want to talk about with the fence, I have my red region. The line exists in this red region. My parabola exists in this blue region. But what about the fence itself? Somebody needs to own this fence. Well, the way that's determined is by who has the bar, the equal to bar in their condition. You can see here that blue has the equal to bar as part of their condition. And so blue actually owns the fence itself. The way we're going to notate this is we're going to put a large closed circle on the blue graph right on the fence. But then the red graph, since it does not own the fence, we're going to notate that with a large open circle. Open circle means that this red line does not own the fence. Closed circle means this blue parabola does own the fence. All right, let's look now at example number 2. So this example number 2 now has 3 rows. There's 3 different equations, all part of this same function. And so my fences, if you look at my conditions, here I'm actually going to need fences at -3, a vertical dotted line fence at -3, and another fence at +2. Now I use dotted lines to show these are not an actual part of the graph. These are just used to determine my regions. So everything to the left of the first fence is going to be this red region. It's going to follow the equation absolute value of x plus 3. Between the two fences is my blue region. It has this constant term 4. And then everything to the right of the second fence is going to follow this equation, -x plus 5. So here the fences have been drawn. And just to kind of make things go quicker, I've written this all out. So my red equation here is an absolute value. And so that makes the V shape. It's going to have a vertex at -3, 0. So I'm going to go to -3, 0. Now, my V shape, if this was not a piecewise function, my V shape would look kind of like this. But since this is a piecewise function, then I know that I'm only allowed to draw this V shape to the left of the first fence. Okay. Now let's talk about this constant term for a second. We haven't done much work with this. This constant term is just simply a 4. It does not have a variable. It's just a constant 4. When this happens, you actually just draw a horizontal line that passes through 4 on the y-axis. So I'm simply going to go to 4 on my y-axis and draw a horizontal line. Now I know that this constant term exists between the two fences, so I'm only going to draw it from here to here. And then lastly, this last equation I did in black, I have this line, -x plus 5. That means that this line crosses the y, has a y-intercept of 5. And then it has a slope of -1. I'm going to write this as a fraction, -1/1. This line goes down 1, right 1, down 1, right 1, down 1, right 1. Keeps following this pattern. Now here, I drew the entire line here. In reality, though, this line is only supposed to exist to the right of my second fence. So let me get out my eraser here. The only part of this line that I'm going to draw is the line really only exists to the right of this second fence. Okay, now let's talk about ownership of the fence. Here you'll see that the red absolute value function owns the fence at -3. So red is going to get a nice closed circle. Blue will get an open circle. And then my bar for the 2 is owned by the blue constant function. So here, the blue will get a nice solid circle on my fence that exists at x equals 2, whereas the line will have to settle for the open circle. All right, so that graph is complete. Now, in example number 3, we are asked to actually evaluate this function at various points. So this means find f of -6 and f of -3. Well, I've already tried to color code this. So anytime you have an input value of x that's -3 or less, anytime x is less than or equal to -3, it's going to follow the red rule. So that's why I've put both of these in red. Now, anytime x is a number between -3 and 2, and we're going to include the 2, it's going to follow the blue rules. And then anytime x is a number larger than 2, we're going to follow the black rule. Okay, that would be our last 2 examples. So getting out a calculator, I'm going to kind of shortcut through this. Here are the answers to example number 3. Notice for f of -6 and f of -3, I have to plug my x value into the absolute value. F of -6 will be the absolute value of -6 plus 3, which is 3. F of -3 is going to be the absolute value of -3 plus 3. It equals 0. So f of -6 and f of -3, I'm going to plug my x value into the red equation. Now, f of 1 and f of 2, with these x values, I'm going to follow the blue equation. Now, the blue equation is just this constant equation of 4. That means, in these 2 examples, f of 1 and f of 2, the answer is just always going to be 4. Okay? That's kind of how a constant equation works. If you try to plug an x into a constant equation, the answer is always going to be the same. The answer is always going to be 4. So this answer is 4, and this answer is 4. Now for f of 4 and f of 10, I'm going to plug my x value into this black line here. If I plug 4 in for x, I do -4 plus 5. The answer is 1. If I plug 10 in for this x here, I do -10 plus 5. The answer is -5. So this is how you can evaluate all of these points of this function using your arithmetic, okay? Using kind of a calculator and plugging the numbers in. Now, I do want you to realize that you can also evaluate these functions. If you have a graph, you can also evaluate these functions graphically. And what I mean by that is, if I look at my graph with an x value of -6, which is right here at my pointer, and then follow it up to where the line actually goes, the v actually goes, this point right here is -6, 3. I can look at this graph and say that when x is -6, the graph has a y value of 3. And so the answer is 3. Likewise here, at -3, this point right here is -3, 0. So I can look at my graph and say f of -3 must be 0. Likewise, f of 1. If I find 1 on the y-axis and follow it to its appropriate graph, this point is called 1, 4 on my graph. So f of 1 must be 4. Likewise, f of 2 is also equal to 4. F of 4, right here, this point is 4, 1. So f of 4 would be equal to 1. And f of 10, this is kind of going off my paper a little bit, but it looks to me like this point would be at 10, -5. So f of 10 would be -5. If you have a graph to look at, you can answer all of these questions graphically. And you'll notice the answers that we got by looking at the graph are the same answers that we would have got using our calculator. You can do it either way. If you have a graph to look at, I'd recommend using this graphical approach. So looking at your assignment, this knowledge should get you through questions 1 through 8. Everything you just learned about graphing and evaluating these piecewise functions, you should be good on. I want to finish this video, I want to look at questions 9 and 10. Question 9, among which intervals does this function f of x increase? Select all that apply. Well, let's look at this particular function. Look at the slope of this function. If we're going from left to right, this function is clearly going downhill from this arrow to 0. That would be called a decreasing function. It has a negative slope overall from this arrow down to 0. But it increases, and it starts to increase from 0 to 1. It's actually constant then from 1 to 2. But then the slope again increases from 2 into the arrow. So from 0 to 1, and then from 2 to the arrow, that's called, we say this function is increasing. It has a positive slope. Now we've learned with interval notation, with the arrow, we kind of represent that with the infinity symbol. And then question 10, using the same graph from question number 9, among which interval does f of x decrease? That would happen from the arrow to the 0. That's the only time this line has a negative slope. That would be represented with negative infinity to 0 using our interval notation. All right, so I hope that is helpful. I wish you the best on this assignment, and as always, let me know if you need any help. Take care. Bye.